Hello, viewers. In today's session, we are going to discuss an important problem from Fourier transforms. And here we are going to find out the Fourier transform of this function f of x that is given as e raised to minus a times the absolute value of x, where a is greater than 0 and x belongs to the set of real numbers, right? So here we are going to find out the Fourier transform of this exponential function. And before finding out uh, the Fourier transform of this exponential function, let us quickly define the Fourier transform of some function f of x. So the Fourier transform of some function f of x is denoted by this notation, that is f of x. So this notation is used to denote the Fourier transform of some function f of x, and sometimes here we write a small f of s, where s is a parameter which may be a real quantity or a complex number, right? So the Fourier transform of some function f of x is given by this integral that is from minus infinity to infinity, and here we have f of x and e raised to minus I times s times x, and here we have dx, right? So here we are using the parameter s, but we can also use other parameters or other letters instead of s, for example k or p, right? So if we take the parameter as k, then we can also write it like this: f of k, and here we have minus infinity to infinity, and f of x and e raised to minus I kx and dx, right? And here we'll prefer this notation. So now substituting the value of f of x as e raised to minus a times a mod of x over here, the Fourier transform of the function e raised to minus a times mod of x is given by f of s, and here we have minus infinity to infinity, and here we have e raised to minus a times mod of x and e raised to minus isx, and here we have dx, right? So now we have to evaluate this integral. So before evaluating this integral, let us first define the mod function. Now the mod function is defined like this: mod of x is equal to positive x whenever x is greater than 0, and mod of x is 0 when x is equal to 0, and mod of x is minus x when x is less than 0. And here we are given that a is greater than 0 and x belongs to the set of real numbers, right? So here we have a minus infinity, and here we have plus infinity, and here we have 0. So here we have towards the left of x is equal to 0, the mod function is defined as minus x, and here towards the right of x is equal to 0, mod of x is defined as positive x. So here what we will do, will split this integral into the sum of two integrals. So the first one is from minus infinity to 0, and then we have 0 to infinity, right? So splitting this integral into two integrals, so when we go from minus infinity to 0, all the values of x are less than 0, so mod of x can be replaced by minus x. So here we have e raised to minus a times minus x, and here we have e raised to minus I times s times x and dx, and here when we go from 0 to infinity, all the values of x are greater than 0, then mod of x is positive x. So here for mod of x will replace mod of x by positive x. So here we have e raised to minus a and plus x, and e raised to minus I times s times x, and here we have dx. So now we can write minus infinity to 0, e raised to here we have simply ax, and e raised to minus isx dx, and here we have 0 to infinity, and e raised to minus ax, and e raised to minus isx, and dx. So now using the laws of exponents here, the base is same, so we have simply e raised to ax minus isx and dx, and here we have 0 to infinity, and e raised to minus here we have minus ax and minus I times s times x and dx. So now we can write minus infinity to 0, and here we can now write a minus is, and here we have x and dx, and here we have 0 to infinity, and here we can now write minus a plus is, and here we have x and dx. And remember, I is the complex number, that is iota, and I square is equal to minus 1. So now we have to find out the values of these two integrals. So let us call this integral as I1 and this integral as I2, right? So here the Fourier transform of e raised to minus a times mod of x is now given by the sum of these two integrals I1 and I2. So let us separately find out the values of I1 and I2 using the method of substitution. So now to find out the value of I1, let us make this substitution, that is t is equal to a minus is, and here we have x, right? So let us differentiate t with respect to x. So we have dt over dx is equal to simply a minus is, because the derivative of x with respect to x is 1. So we have dt is equal to a minus is, and here we have dx. Now here the limits of integration vary from x is equal to minus infinity to x is equal to 0. So when x tends to minus infinity, then from this result or this substitution we can easily make out that t tends to minus infinity. So when x approaches to minus infinity, then t approaches to minus infinity, and when x tends to 0 here, then t also tends to 0, because when we take x is equal to 0 over here, then t also tends to 0. So now we can write this integral I1 in terms of t. So we have here a minus infinity to 0, the limits remains the same, and here we have e raised to t, and for dx we can now write dx is equal to dt over a minus is. So here we have dt over a minus is. So now taking 1 over a minus is outside the integral, we have minus infinity to 0 e raised to t and dt. So now this is a simple integral, so we have 1 over a minus is, and here the integral e raised to t is simply e raised to t and minus infinity to 0. So now let us substitute the limits, and taking the difference we have e raised to 0 minus e raised to minus infinity, right? Now e raised to 0 is equal to 1, and e raised to minus infinity, it tends to 0, because we know that e raised to minus x, it tends to 0 when x tends to infinity, right? So because here e raised to minus infinity can be written as 1 over e raised to infinity, and e raised to infinity tends to infinity, so this expression it tends to 0, right? So here we have now 1 over a minus is and 1 minus 0, right? So this is simply 1 over a minus is. So here the value of I1 is given by 1 over a minus is. So now let us find out the value of I2. So now to evaluate this integral I2, here we'll make this substitution. T is equal to, here we'll write a plus is and x. So now differentiating t with respect to x, so dt over dx is a plus is, and here we have now dt is equal to a plus is times dx. So dx is equal to dt over a plus is. Now here the limits of integration vary from 0 to infinity. So when x is 0 or x tends to 0, then the value of t also tends to 0 or t is equal to 0. And here when x tends to infinity, then t also tends to infinity, right? So now here we can write this integral I2 in terms of t. So the limits remains the same, so 0 to infinity, and here we have e raised to minus t, right? Because t is a plus is times x, and for dx we can now write dt over a plus is. So now taking 1 over a plus is outside the integral, we have 0 to infinity and e raised to minus t and dt. So now we have 1 over a plus is, and the integral of e raised to minus t is minus e raised to minus t, and limits of integration are from 0 to infinity. So here we are using the two standard results, that is e raised to theta d theta is simply e raised to theta, and e raised to minus theta d theta is minus e raised to minus theta, right? So now here substituting the limits and taking the difference, we have 1 over a plus is, and here we have minus e raised to minus infinity, and then we have plus here and e raised to 0. So now here we can write e raised to minus infinity, it tends to 0 as we have just explained, and e raised to 0 is equal to 1. So we have now the value of I2 as 1 over a plus is, and here we have minus 0 plus 1. So this is simply 1 over a plus is. So now the value of the integral I2 is 1 over a plus is, right? So now the Fourier transform of this function f of x is given by the sum of these two integrals. So let us add these two complex numbers. So here we have a minus is times a plus is, and here we have a plus is plus a minus I times s, right? So now we have here a plus a is 2a, and here these two terms get cancelled, and here we have a minus b, a plus b, that is the standard identity. So here we have a square minus I square and s square, that is equal to 2a divided by a square plus s square, because I square is equal to minus 1. So viewers, the Fourier transform of this function is given by 2a divided by a square plus s square. So this is the desired Fourier transform of this function, right? So here we can make two important deductions. If we take a is equal to say 1, then here the Fourier transform of e raised to minus mod of x can easily be calculated by simply substituting a is equal to 1 in this result. So we have 2 times 1, and here we have 1 square plus s square. So that is simply 2 divided by 1 plus s square. So the Fourier transform of e raised to minus absolute value of x is given by 2 divided by 1 plus s square, where this x belongs to this interval. Similarly, if we take a is equal to half in this result, then the Fourier transform of the function e raised to minus half mod of x is given by f of s, that is equal to 2 times 1 over 2 divided by, here we have half square plus s square. So here 2 and 2 get cancelled. So we have 1, 1 over 4 plus s square, and simplifying this, we have 4 divided by 1 plus 4 s square. So the Fourier transform of e raised to minus half times mod of x is given by 4 divided by 1 plus 4 times s square. So here this result can be taken as a standard result in Fourier transform of functions. So the Fourier transform of the function e raised to minus a times the absolute value of x is given by 2a divided by a square plus s square, and assigning particular values to a. For example, here a is equal to 1. The Fourier transform of e raised to minus absolute value of x is given by 2 divided by 1 plus s square, and if we take a is equal to half, then the Fourier transform of e raised to minus half times mod of x is given by 4 divided by 1 plus 4s square. And similarly, assigning other values to this parameter a, we can easily find out the Fourier transform of the corresponding exponential function containing this term, that is minus a times the absolute value of x.